Well, hello everyone. Consider a box at rest on a floor, and the box has some friction with the floor. What would I have to do in order to get the box to accelerate uniformly? That means move with a constant acceleration, remembering there's some friction. Well, obviously, if I want the box to move at all, I have to apply an applied force, right? But there is some friction, so if I want it to accelerate, I have to apply a force that's larger than friction. And if that force is constant, then that will give rise to a uniformly accelerated motion. And that's what we know linearly, right, about acceleration. We know that it takes a net force to make something accelerate. And therefore we know Newton's second law, right? Net force is mass times acceleration. But how does this work with rotation? Is there a similar kind of math model that we can use to discuss why things move with a uniform angular acceleration? Well, think about the lab equipment that we've used. And if you want to get it to accelerate, you have to apply a force at some distance from the axis of rotation so that that force applies a torque. And that torque would, of course, make things angularly accelerate. So we need to have a net torque to make things accelerate. What factors do you think are going to affect how quickly it will angularly accelerate? Well, I think the obvious one, of course, is how much torque you apply. Right? If you apply more torque, I think you would expect it to spin faster. And the other one's a little bit trickier. Right? Now, you might think with the linear analogy, right, it would have something to do with the mass. But as with pretty much everything in rotation, it's a little more complex than that. We're actually going to do a series of a couple different labs in order to figure this out. But it is something to do with the mass. Right? It's something about the mass. In order to make that not part of our lab that we're going to do here, we're just going to keep everything about the mass constant during this lab and tease it out during the post-lab. So the purpose of the lab that we're about to do is really to come up with a Newton's second law for rotation. But we're going to create graphical and mathematical representations of the relationship between the torque and the angular acceleration for a system with constant mass. We're not going to change the mass at all. We're not going to change where it is. We're not going to change how much of it there is. We're just going to leave all mass things the same, all right, so that we can figure out what that's going to be later. So really here we're doing torque and angular acceleration. Okay? So, how are we going to find the angular acceleration? Well, you're going to open up a Data Studio file, and on it is going to be a big graph of angular velocity versus time, and that's the only graph there is. And you've seen this kind of graph being made with the equipment, right? Once we take the string and wrap it around the larger pulley, put a certain amount of mass hanging off the side, off the other pulley, we let it go, it's going to angularly accelerate, it's going to create an angular velocity versus time graph. And if we want to see the angular acceleration, what do we look at? Yeah, the slope. All right, so you will select a part of the graph, right? The part of the graph where it is angularly accelerating. Please get rid of the schmutz at the beginning before you let it go and the schmutz at the end after it hits the floor, right? And then deal with the slope of that graph, right? Select it, linear fit. It's already turned on actually when you turn it on, right? But make sure you select the part of the graph you want every trial. The tough part here is the torque. Right, so we have to talk about how we're going to find the torque. Well, this is a picture of the equipment, kind of. There is one extra little thing about this pulley over here that I don't really like about this picture, but I'll show you a different one in a moment. Right? But this is our bar, our rotary motion sensor, our bar with the two masses, and we're not going to change those masses, and we're not going to change where they are. Unlike this picture, we're going to put them flush with the end, just so that if they fall off or something gets moved, you can put them back, right, to where they were, so we don't change the mass at all. You're going to wrap the string around the biggest pulley and let it come off to the hanging masses right on the side. So we want to talk about the torque that's being put on this apparatus here. Right? Well, we know the torque is Rf sine theta. But what's R, what's F, and what's theta? Well, R will be the radius of the pulley, because the string is going to be applying a force on the outside of the pulley. And we're going to use the biggest pulley, and that radius is on your lab sheet, right? So that's a known, that's based on the equipment, and I've just given it to you, whatever it happens to be. It's not that big, it's a couple of centimeters, but right, it's right on your lab sheet. F will be the force of tension in the string. How are we going to figure that out? Well, we'll get to that in a moment. This is a process in this lab. So then the question becomes, well, what's theta? Right? Theta, remember, would be the angle in between r and f of t. It's the angle in between the two vectors. Well, this is probably a better view, at least from the top down, of how the equipment will look. I want you to notice here, right, that r would be the distance from the axis of rotation to the point of application of the force, right, where the string is coming off of the pulley. So this is r, right? It's that distance. Ends up being the radius of the pulley, at least to the inside groove, which is what I'm giving you on the lab sheet. But notice here how this pulley is tilted, right? And it's tilted so that the string comes off tangent to the big pulley. If you wrap it around the largest pulley, comes off tangent, and then the string falls right across this pulley to keep everything all lined up. If you actually put it this way, where it's kind of perpendicular to the apparatus, it really the string doesn't stay on. The string kind of falls off because it's off to the side when you're using the bigger pulley. In this picture, they're using the really small pulley. Okay, but since we're using the bigger one, we need to tilt this one. Okay, that should be the way it's set up now, but if you need to move things around, right, you should tilt it that way. Okay? So the thread runs tangent to the point where it leaves the three-step pulley, the biggest pulley on there, and straight down the middle groove of this pulley. Now that means if the string is tangent, then what's the angle? Right? The angle is 90, and the sine of 90 is 1. So we can calculate the torque if we take the radius of the pulley times the force of tension in the string. That doesn't seem so tough. Complication comes in with, what's the force of tension in the string? Well, let's start out with a force diagram of the hanging masses. What forces act? Well, you've got a force of gravity acting down, and of course you've got a force of tension acting up. How big are those forces? This is one of the common mistakes when doing problems like this in APC, is that people will say, oh, they're equal. But if those forces were balanced, and those are the only two forces, what kind of motion would you end up with? You'd end up with a constant velocity, no acceleration, right? Because the forces would be balanced. Well, right, here we have the force is not balanced. It is accelerating. In what direction is it accelerating? The masses are accelerating downward. So which force has to be bigger? The force of gravity. Right? So the force of gravity is going to be bigger than the tension because the masses are accelerating downward. That's a very important little conceptual point to pick up on problems like this, which are kind of common little problems in APC rotation. So if we want to figure out the tension, we've got to use Newton's second law. The net vertical force is equal to the mass times the vertical acceleration. This, by the way, is the linear acceleration, right? This is an A, not an alpha. This is an A. Well, in this case, we've got two forces. We've got F of t up and F of g down. So that would be F of t minus F of g. And we got to be careful here. Notice I'm getting rid of all of the arrows. I'm turning this into a scalar equation. And so it's accelerating downward, so the acceleration is also negative. With me here, folks? Because a lot of times there's some negative issues here too. So F of t is up, F of g is down, the acceleration is down. So we get F of t minus F of g equals negative ma. So the force of tension is the force of gravity minus ma. And as we well know here on the surface of the Earth, the force of gravity is mass times our local gravitational field strength. And if you want to factor out an m, right, we see that we can calculate the force of tension by taking the mass times the quantity, gravitational field strength, minus the acceleration. Now this is the linear acceleration of the masses. Well, we currently don't have the linear acceleration of the masses. So how are we going to find that? Right? How are we going to find the linear acceleration of the masses? Okay, which is what we need here to figure out the force of tension to figure out the torque? Well, first thing we need to realize is that we are going to assume, and this is a good assumption with this equipment, that this is a perfect situation where the string doesn't slip on the pulley. Okay, the string doesn't slip on the pulley. Now, if the string doesn't slip on the pulley, what has to be true about the acceleration of the masses and the string, right, that they're attached to, and the linear acceleration of the outside of the pulley? Let me say that again. The acceleration of the masses and the linear acceleration of the outside of the pulley. Well, if the string is going to come off the pulley without slipping, right, those have to be the same. You with me there? Right? The acceleration, linear acceleration of the masses, these are A's, not alphas. The linear acceleration of the masses has got to be equal to the acceleration of the outside of the pulley due to the tension in the string, and the tension in the string is tangent, so the acceleration of the outside will be tangent. So, if we can find the acceleration of the outside of the pulley linearly, then that would be the same as the acceleration of the masses. And since it's the tangential component of the acceleration, we know how to find that. We derived that in class. That is angular acceleration times the radius. So there are all the pieces. And you'll see columns on your data sheet for all of these. So we're going to use the slope of the angular velocity time graph to find the angular acceleration. That and the radius of the pulley will give us the tangential acceleration of the outside of the pulley, which is also the linear acceleration of the masses because the string is not slipping. With the acceleration of the masses, we can then find the force of tension in the string, and with the force of tension in the string and the radius of the pulley, we can find the torque. And once we make all those calculations, we can then graph torque versus angular acceleration. I want a graph of torque on the vertical axis and angular acceleration on the horizontal because I need the slope to mean something. Okay? So this lab has a lot of calculations. I've put these equations on your lab sheet to help you out. I've put what all the variables are on your lab sheet to help you out, right? And I've tried to put them in some sort of order in the data table so that you calculate one, you go to the next, you go to the next, and so on, right? But keep in mind that all of this is just a very clever little high-tech apparatus to allow us to measure the angular acceleration and the torque, right? So that we can see what their relationship is. So this is how we're going to do this Newton's second law for rotation lab.